Our first example today is going to deal with basic higher order derivatives. So if we start off with the function f of x is equal to negative 2x to the fourth plus 9x to the third minus 5x squared plus 7, our example A, we have to find the derivative of f of x. And in order to do that, we're going to use the power rule. So we know that f prime of x, which means the derivative, is equal to negative 8x to the third plus 27 x squared minus 10x. So that would be the first derivative. Part B is asking us to find the second derivative of f of x. When you find the second derivative, that means you're taking the derivative of the original twice. But since we've already done it once in part A, finding the second derivative is the same thing as finding the derivative of f prime of x. So f double prime of x is going to be the derivative of f prime of x, again using the power rule, negative 24x squared plus 54x minus 10. Awesome, and this process continues all the way until nth derivative, so you could keep doing this as many times as you wanted to. Part C, the third derivative of f of x, which again is the derivative of f double prime of x, so f triple prime of x is equal to negative 48x plus 54. Good. Part D, again, find the fourth derivative. So again, we're finding the derivative of f prime, f to the third. So this time, when we do the fourth, we have to put the 4 in parentheses. When you're doing the derivative, they must contain the parentheses. And that's equal to negative 48. And last but not least, finding the fifth derivative, f of 5 of x, that is equal to just 0 because the derivative of a constant is 0. Example number 2, or just another application of it. If we have f of x is equal to 1 over x, find f the second of x. And then we also have to find, so we first have to find f prime of x. I'm going to change f of x so it's read as x to the negative 1. So f prime of x using the power rule, negative 1, x to the negative 2. F double prime of x, again, the power rule, 2, x to the negative 3. And then the third, negative 6, x to the negative 4, which is the same thing as negative 6 over x to the 4. Perfect. The last part of the question is, when we take the nth derivative, will it ever be equal to 0? And the answer is no, because it is a rational function. We're going to apply higher order derivatives when it comes to position, velocity, and acceleration functions. All right, so s of t represents position function, and that tells you where a particle or a car is located. When you take the derivative of it, the first derivative, that's the same thing as finding the velocity function, the first derivative of position. That's telling you the speed of the car. S double prime of t, which is the derivative of the velocity function or acceleration, is the acceleration function. And again, this is the second derivative of position. And then you can just go into a little bit more depth, saying that position function is the measure of length, so foot, meters, kilometers. Velocity is the first derivative of position. If it's bigger than 0, then it's moving right or up. If it's less than 0, it's moving left or down. If it's equal to 0, the object is still or it's changing directions. So this is distance per time, so miles per hour, feet per second. And the absolute value of your velocity function is your speed. Acceleration is the second derivative of your position function, or the first derivative of your velocity function, and it's distance per time squared, so meters per second squared. Our last example, example 3, we have the position of a particle is given by the equation s of t is equal to t cubed minus 6t squared plus 9t, where t is the time in seconds and s is the position in meters. So our first one is find the acceleration at time t. Acceleration is the second derivative of our position function. So we have to find s prime of t, which is the same thing as our velocity. And that's using the power rule is 3t squared minus 12t plus 9. Then we have to find the derivative of that, or the v prime of t, your acceleration function, and that's going to be 6t minus 12. Since we found the second derivative, that is our equation for acceleration at time t. Now, part B is what is the acceleration after 4 seconds? Since we now have an equation for acceleration, we can plug 4 in for t. So a of 4 is equal to 6 times 4 minus 12, which is equal to 12 meters per second squared. And then last but not least, it's asking us if the particle is moving up or speeding up or slowing down. Since our acceleration is 12, which is bigger than 0, so since a of 4 is greater than 0, the particle is speeding up. And last but not least, in your homework, you'll have a question that says, find where the horizontal tangent line, or find where the tangent line is horizontal. A horizontal line has a slope of 0, so in order to do this, you have to find the derivative, you're going to set it equal to 0, and then solve, and most likely by factoring. Nice job today.